So in this clip, we're going to take a look at how block diagonal matrices work, or rather operators whose matrices are block diagonal. So a block diagonal matrix is a square matrix where the diagonal, there's zeros below the diagonal and above the diagonal, but not everywhere below the diagonal and everywhere above the diagonal. So in other words, you know what, this is going to look better if I draw a little picture. So it's going to look something like this. So here's an example. Suppose we have the matrix. We can divide it into some zones like this, and let's see, so thin, wide, medium, and then wide-ish. Okay, so something like this. And then the idea then is that everywhere outside of these blocks, and so these blocks, they each of these blocks is not necessarily just one entry. It could be a sizable little rectangular matrix, right? And so the idea is all these ones I'm shading in are going to be 0, but then these square matrices or square submatrices along the diagonal are the only places where you're going to find non-zero entries. Okay, so everything blue is a 0. And so it could be the case that this one right here, this little box, that actually might be, say that's like a 3x3 matrix, and this one here, this one might actually be like a 5x5 or whatever, something. But they're bigger than a 1x1, so they're not just single entries. Okay, so that's what a block diagonal matrix looks like, something that can be written like that. So now theorem 8.29 says that if we're over a complex vector space, then if lambda 1 through lambda m are the distinct eigenvalues and they come with multiplicities d1 through dm, then this implies that V has a basis in which the matrix of A is going to be block diagonal, and there's going to be m blocks coming down here. So this corresponds to the number of different distinct eigenvalues we have here. And then each block is going to be a square matrix like this, which is upper triangular, and the diagonal is constant. So this is the same lambda j all the way down. And so in particular here, the dimensions on this, since this is going to be square, this is going to be a dj by dj square matrix, where the dj is coming from this list over here. Okay, now I should point out also that the book gives you the forward direction. It does not mention the backward direction, but I'm going to give you a proof of why these are actually equivalent, or at least a bit of a sketch of one, because I think the picture is really helpful in the reverse direction for understanding why this works. It kind of shows you the structure a little bit more in the backward direction, I think. So let's go ahead and prove this. So for the forward direction, following the book, if we look at 8.21c, so this is our direct sum decomposition of V in terms of generalized eigenspaces, then T minus lambda J I, when restricted to the generalized eigenspace, is nilpotent. That's the third part of that theorem. So then that means that this generalized eigenspace, so this subspace, has a basis in which the matrix is strictly upper triangular. And I forgot what number this one is, but it's the last one in section 8a, and it shows you that it looks something like 0 down the diagonal, 0, and then star up here. Yep. Okay, so then the idea is if we look at this T minus lambda J I restricted to G lambda J, and then we add the diagonal back on, and I guess this should be restricted to GJ back as well. Then what did we do? Well, this means we just put lambda J all the way back down the diagonal of this matrix right here. So that means that this one has the form of AJ now as given in the statement. Okay, and so then combining these bases, it gives a basis for V in which A has a block diagonal form. So we get a basis because, as we saw before, and talked about before, the generalized eigenvectors for different eigenvalues are linearly independent, right? And so this is, I guess, leaning on also 821A. All right, so now let's see, if we talk about how to go in the reverse direction, then let's see, so suppose A is block diagonal. Then the blocks correspond to invariant subspaces. And this is basically coming by the definition of matrix multiplication. And so let's see that again. So if I've got some matrix here, something like this, and let's see, so I'm going to color in the zeros again as blue. Right, and now let's look at how this multiplies a vector from our space here. So we've got stuff corresponding to the same rows where the block diagonal matrix has its definition. So now let's take the purple block right here. Well, now when we do matrix multiplication, so like rows from this first part up here are going to hit stuff here, and any of these zeros are going to kill off anything from down here. So in other words, none of this data down here factors into the computation of telling you what you get in the output over here. So in other words, when you do matrix multiplication and you multiply a row with a column, it's going to be numbers from the purple zone multiply with numbers in the purple zone. And where are they going to come out? They're only going to come out over here in this first block. Now, similarly, when we look at what's going on in the next zone here, it's going to meet up with this part here and map over to here. Because when you do rows from in this region and you multiply against columns over here, these zeros are going to kill off anything in the purple part. So the purple does not factor into the computation. And these zeros are going to kill off anything that comes from down here. So nothing from down here is going to factor into the computation. And then since we're doing rows at this level, we're talking about outputs at this level. So the orange combines with the orange to give you more orange, but it doesn't give you anything here or here or here. And it doesn't take into account data from up here or here or here in that calculation. And same thing for the green. And same thing for the yellow. And so you can see that the fact that this square block, like, so if we're looking at this orange block right here, when I said that it corresponds to an invariant subspace, that's because this input data picks up this input data right here. And then since it's sitting in these rows, it gets sent to this column data out here. And so we just go straight from orange to orange. So here, we're used to drawing things like this because that's how we write matrix multiplication, but maybe a different picture of the same process is more helpful. So this is a picture of the transformation T as seen through the eyes of its matrix. And so you can see that this subspace gets mapped back into itself, and this subspace gets mapped back into itself, and this subspace gets mapped back into itself, and if I can find yellow, this one does as well. So it's like the rainbow bright of invariant subspaces going on here. Okay, so now what does that tell us? So now we're also, since we're assuming that we've got this block decomposition, and we're assuming that each block looks like lambda j's, like all the same lambda j down the diagonal, and then 0 here, and then whatever it wants to be above the diagonal. Then if we look at aj minus lambda ji, then we're going to be subtracting those lambdas off the diagonal, and we're going to end up with something that looks like zeros down the diagonal and below the diagonal, and then still whatever it wants to be up above. And so we can see that has the form of a nilpotent matrix again, and the standard form, say, of a nilpotent matrix. And if we take a minus lambda ji and we raise it to the power dj plus 1, that's going to be the minimal power needed to make this matrix into the zero matrix. Okay. And so then all that needs to remain is notice that since M is an algebra isomorphism between linear operators on V and the square matrices. And so when I say it's an algebra isomorphism, what I mean is that if you put the results 336, 338, 343, and 360 all together, it tells you that you have an isomorphism of vector spaces, and it's also satisfies multiplicativity, right? So M of ST is the same as M of S times M of T with matrix multiplication, yeah? So all that together gives you an isomorphism of algebras. And since you have an isomorphism of algebras between these two things, all these results that I was talking about A, carry over to being results about T as well. And so, like, in particular, if you look at this guy right here, this is saying that T minus lambda Ji is nilpotent, so that lambda J is an eigenvalue of multiplicity dj. And that does it for our proof.